TCP is by far the most complex protocol in the TCP/IP protocol suite. Most of the really hot traffic runs over TCP. For example, your email traffic, your web browsing traffic, your file transfer traffic of any kind will most likely run over TCP because TCP has all the sequencing and acknowledgement and retransmission stuff all built into it. The first file we're going to open up is called FTP-dir, and it's simply someone making an FTP connection to a server. They are logging in. We can see the username on there because everything's clear text and FTP communications. But we're going to be focusing on the TCP header and the TCP header structure as we look at this trace file. Now, packet number 3 is the first TCP packet that we see. This is part of the three-way handshake where we see SYN, SYNAC, ACK. I'm going to collapse the Ethernet header, and I don't care about the IP header except for the fact that in the IP header, when the protocol field is set to 06 or decimal 6, that means that a TCP header is coming up next. Here are the fields of the TCP header. First of all, we have the source port and the destination port fields. Then we have a sequence number. Now, even though my system says the sequence number is 0 here, you can see down below in hex that it's not. Wireshark is putting in a relative sequence number to make it easier for us to visually analyze the communications. The sequence number is one of the pieces that we use to track the sequence of packets. Every time I send a packet out, I set a sequence number. And if my sequence number is at 10 and I'm sending out 10 bytes of data, the next sequence number for me would be 20. The sequence number is always the last sequence number plus the last amount of data sent. Now, Wireshark is putting a sequence number of 0 in there, as I said before, just to make it simpler for us to read the header. The header length field will tell us the length of just the TCP header. This TCP header is 24 bytes long. The typical TCP header on data communications will be 20 bytes long, but during the handshake process we negotiate options, and that's why this header is longer. Now we have the flags field. Now in the flags area, I'll open this up. We have an area set up for congestion recovery. So we have a congestion window reduced setting. We also have an early congestion notification echo bit that's available. Now, most of the time you're not going to even be dealing with these two areas. The majority of the time you'll be dealing with these 6 different flags in the TCP header. The first flag is the urgent flag. If this flag is set to 1, then we'll have an additional field in here, which is the urgent pointer field, that will tell us where to start reading the data first. The acknowledgement bit. If we have this set, it basically means that we're acknowledging receipt of some information from the other side of the communication. The push bit. If the push bit is set on outbound communications from a system, it means that the data can't sit in the TCP buffer area waiting to go out. It's got to go out immediately. This is typically time-critical communications or very user-interactive communications, such as perhaps Telnet. Reset is a refusal or a shutdown of the TCP connection. SYN stands for synchronize the sequence numbers. The SYN bit should only be set in the first 2 packets of the handshake, as each side decides what their starting sequence number value will be. And the FIN bit simply means that I'm finished with what I'm doing, done with that, but I'm not explicitly shutting down the connection. The window size field is the sender's way of telling the other side how much receive buffer space they have available for TCP communications. Later on, when we look at the unusual TCP traffic, you'll see a system that has run out of received buffer space, and it begins advertising a window size of 0. We also have a checksum area. Now, just a note on TCP communications. If you're running Wireshark on the network, and you're listening in on your traffic, and you're listening in on your own traffic, and you keep getting TCP checksum errors with every single packet, don't just assume that you have a problem in your TCP stack. Most likely, your system is doing checksum offloading, which means that the checksum is being calculated by the network interface card, not by the TCP stack itself. So that means that Wireshark is not able to see the checksum value. So it'll come up and everything will be TCP checksum invalid, TCP checksum invalid. If that really irritates you, you can go into the Preferences area under the Protocol section and turn off checksum validation for TCP communications. I'll open up the checksum area, and here you'll be able to see that we have those regular values for checksumming. Checksum is good, then this value is true. Checksum bad, it's false. And in the filtering section, we'll filter on good and bad checksums. Then we have the Options section. Now the Options section is visible to us only typically in the first 2 packets of the handshake. Now this handshake only has one option in it, saying that the maximum segment size is 1460 bytes. Now that value may seem too small, but that's actually correct for TCP communications going over an Ethernet network. We have 1460 bytes of payload allowed, plus we typically will have a 20 byte TCP header, that brings us up to 1480 bytes, plus we typically will have a 20 byte IP header, that brings us up to our 1500 bytes that we're allowed to have inside of our Ethernet 2 frame. Now as we were looking at this packet, I highlighted the sequence number field, and you can see it highlighted down below. When I went to the next field, the header length field, you notice that we skipped these 4 bytes right here. These 4 bytes are not used during the first handshake packet in the handshake sequence. The SYN packet only will not use those 4 bytes. But we will see another field pop up when we look at the SYNAC packet. Packet number 4 is the SYNAC packet. And now, after the sequence number field, we now have a field called the acknowledgement number field. The acknowledgement number field is the other side's next expected sequence number. So this system is saying, I believe that the next sequence number I will receive from you will be 1. This side of the communication has set its sequence number at 0. At least it's the relative sequence number of 0. Down below we can see what the actual sequence number is. Sometimes it's helpful when you're just learning TCP to turn off the relative sequence number process so that you can see exactly what the sequence numbers are and see that each side establishes its own sequence number at the beginning of the handshake process. There's another strange thing that happens in the handshake process. As I mentioned before, in packet number 1, our sender has set a sequence number value that Wireshark is just translating at 0 to make it easier to count. This sequence number value should count up based on the number of data bytes sent out on the cabling system. There are no data bytes in the first packet of the handshake, and yet the next time 10.3.71.7 communicates, it increments the sequence number by 1. The same thing will happen to the device on the other side of the communication. 10.3.30.1, it begins at sequence number 0, and the next time it communicates, it will be at sequence number 1, even though it hasn't sent any data packets across the wire. And the reason for that is at the beginning of the communication, we have a phantom byte. We have a phantom byte that is theoretically sent from each device during the first 2 packets of the handshake process. So that's the only time really when it looks very, very strange. Sometimes you'll also see the phantom byte though during a teardown sequence of a connection. But this is where you'll most likely see it. And it can be very confusing because if you just learned that the sequence number only increments when data is sent, and by the amount of data sent, why is this incrementing by 1 between the SYN packet going out and the next packet that this device sent out? And it's that horrible, horrible phantom byte. Now in the first packet of the handshake process, we saw that there was a single option setting the maximum segment size at 1460 bytes. We'll go to the second packet of the handshake option and see what options have been set there. I'm in the second packet, and here we can see that the other side has set a maximum segment size of 1460 bytes. And now Wireshark's sequence and acknowledgement system comes into play. This is fantastic. It gives you the ability of associating all of your TCP packets to each other and measuring the round-trip time between sending a packet to someone else and getting the acknowledgement back. On a network with a lot of traffic, this line right here that links us to the related frame is invaluable. Because if we have a lot of traffic and we find out that the handshake packets are not right in order, there are all these different packets in between, we can look at one of the packets in the handshake process and double click on it, and it will take us to the frame that's related to the packet we were viewing. Looking back at packet number 2, we can also see that the round-trip time value is listed for us. This is something we can filter on. And when you get to the next section where we're filtering on TCP traffic, this is one of the filters that you will build, a round-trip time ACK filter. So that is the basic structure of the TCP IP or the TCP header. In the next section, we'll go through building capture filters for TCP traffic, a standard display filter for all TCP traffic, and then display filters based on an individual field, as well as an individual bit value, as well as the analysis information that Wireshark provides. Now we're going to build a series of filters. The first filter we will build will be a capture filter for all TCP traffic. Then we'll go into building display filters for all TCP traffic, and then we'll build more specific filters based on TCP fields and the TCP analysis information that Wireshark provides. To build my TCP capture filter, I'll select the Capture Options window. I have an existing filter defined in there called UDP, and I'm going to get rid of that. And I'll look at the available capture filters. You can see that one is already created for you for TCP only. That's already set up. When you download Wireshark, you should be able to have this filter already in place. So we don't need to do anything else to build that TCP filter. I'll click OK, and I'll click Start to begin capturing traffic. Now I'm capturing traffic in the background, but I have no TCP traffic running. So I'm going to toggle over to a browser window and make some HTTP communications run across the cabling system by browsing to some websites. I've just browsed over to the Wireshark web page, and from here I'll go over to the wiki page. Now that should be enough to give us some TCP traffic in the background. There's our TCP communications. We can see the handshake that it begins with. We can see the GET request going out. So we know that our filter worked properly. Now I'm going to stop capturing, and I'm going to open up an existing trace file that has a number of different types of communications, not just FTP communications. I'll continue without saving. And the trace file I'm going to open up is called nessus.pcap. There we can see some ICMP traffic, some UDP traffic, some DNS traffic, and some TCP traffic in there. It's very simple to build a TCP filter. All we have to do is type in TCP in our display filter window, click Enter, and now we're just looking at TCP traffic. But maybe I want to filter on something in particular. I see these reset packets going out on the cabling system, and I want to know how many packets in this whole entire trace have reset, the reset bit set. So I'm going to open up an existing packet that has the reset bit set to 1, and I don't care about the ACK bit, so I'm not going to right mouse click on the summary line for the flags, because if I did that it would get all packets that have both reset and ACKs and the ACK bit set. Instead I'm going to go down to the individual bit for reset, right mouse click, prepare this filter based on the selected value. We can see the syntax, tcp.flags.reset ==1. Remember that as you look at your Wireshark communications, if you were to click on a field, you can look down in the very bottom area here at the status line, and it will tell you the name of the filter that would go with that field. So we know that if we wanted to filter on the ACK bit set to 1, the TCP flags it would be tcp.flags.ack ==1. Same thing with SYN, tcp.flags.syn ==1. I'll apply my filter now. And now all I'm looking at are the number of resets that are taking place. Looking down in the status window, I can see that out of 2,021 packets, I have 665 resets, and that's not very good. Resets are typically seen as a way of refusing service. If someone tries to make a handshake and you don't support that service, you send back a reset, but they also can be used to tear down a connection. If we have way more resets than we have SYN packets, then they aren't being used to tear down connections. They're actually probably the responses to some sort of a TCP port scan. Now, besides doing filters for individual fields inside of the TCP header, we can also build filters based on the TCP analysis information. So for example, here I have the round trip time to ACK the segment was and a value. I can click on this and then right mouse click and say I want to prepare a filter based on the selected value. Now we can see that we have a filter called tcp.analysis.ack_rtt for round trip time is equal to this value. Now I probably don't want to try to find another packet where the round trip time was the exact same amount. I might want to look for higher round trip times, such as a round trip time of 0.1. I'll click apply, and we can see that we have one packet where the round trip time was greater than 0.1 seconds. I'll scroll down here, and we can see the round trip time to ACK the segment was 42.44 seconds. And we can see that we have an analysis flag here saying a segment before this frame was lost. Now, as I'm highlighting this line where it says a segment before this frame was lost, if you look down in the status line, you can see that we actually have a display name or display filter name that we can use to locate all lost segments. I'm going to right mouse click on this line and say I want to prepare a filter based on the selected value, TCP analysis lost segment. I'm going to apply this, and now it's showing me all of the packets where the previous segment was lost in the trace. Let me take you out to where you can find the master list of all of the display filters possible for TCP communications. I'm on the Wireshark web page, and I'll select Documentation, and then I'll scroll down to the Display Filter Reference area, click on the link. There's the index, and I'm interested in TCP filters, so I'll click on the letter T. There's TCP. I'll click on the link, and now these are all of the display field names that we can use for TCP communications. In course number 1 of the Wireshark University course set, Fundamentals and Functionality of Wireshark, you saw me work a lot with these analysis fields, not only in filtering, but also in building charts and graphs. So here we can see there's our TCP analysis ACK_round trip time. We can also pull out all the duplicate acknowledgements, see all the fast retransmissions, as well as build filters just based on our individual field values. We can also find zero windows, window probes, where a window full condition took place. So there are so many things you can filter on for TCP communications. Another place you can go to find what's possible for doing display filtering would be the expressions area. I'll click the expressions button, and in the expressions window I'm going to type TCP. I'm down at the TCP protocol stack now, and I'll open that up and see what's possible for filtering for TCP communications. Here we can see the TCP port, and we can say whether the TCP port is present, the source port is present, or it's equal to a certain value, or it's not equal to, or it's greater than, less than, greater than or equal to, less than or equal to. And as I scroll down, we can see all of our analysis display filters listed in here as well. You will probably spend a fair amount of time working in the area of TCP communications when you're troubleshooting a network. The reason is that when we come to a network that's having problems, we want to validate that the network itself is not at fault, that we're not having big latency values or we're not having packet loss. We want to know whether it's the application at fault or it's the network at fault. And doing TCP analysis is the way that we can separate the two. In this module, we're going to look at normal TCP communications. I've opened up a trace file called ftp-dir.pcap. We can see the communication begin with the handshake process. The first packet of the handshake is the SYN packet, then we have SYNAC and ACK, and that's a normal handshake process. In the SYN packet, we see that the client system is sending the packet out to the FTP port 21, and we also see that the client has defined its maximum segment size as 1460 bytes. That's the amount of data that can sit after the TCP header. That's a TCP segment. This number is correct for an Ethernet network because 1460 bytes plus the 20 bytes of the TCP header plus the 20 bytes of the IP header gives us our 1500 bytes, which sits inside of our Ethernet frame that has 18 bytes. And that brings us up to our 1518 number. Now I have the relative sequence number process turned on in Wireshark. This means that it will start the sequence number for both sides of the communication at 0. It's much easier to count up that way if we start at 0 instead of the really long number that we would get if we used the actual starting sequence number. But if we're placing two analyzers on either side of a router, for example, and we're capturing the traffic on one side of the router and the other side of the router, and we want to compare them, we might want to use exact sequence numbers, especially if we didn't catch the beginning of the communication transfer. Then we definitely want to turn off the relative sequence number process. You can turn that off by going into Edit Preferences. In Preferences, we would select Protocols and TCP, and this one is the one where you can turn it off right here, Relative Sequence Numbers. If you turn that off, you're also turning off window scaling. We'll talk about window scaling in a moment. There's also the ability to turn off the analyzing of sequence number information, but I leave that on because I want to see when I have missing segments, problems in the communication such as retransmissions. So I'll close this window. Now the first packet of the handshake contains no data, although in TCP communications during the handshake process we have something called a phantom byte. It's as if this 10.3.71.7 actually sent 1 byte of data across to the other side when it set the SYN bit on. And when the SYNAC came back, it's as if there was 1 byte of data sent in that packet, even though there was not 1 byte of data in that packet. It's because of this that the sequence number will increment when we get to the third packet of the handshake process. Suddenly we see 10.3.71.7, our client, saying that the sequence number is now 1, indicating that 1 byte of data was transferred with the last packet. That's the phantom byte, and you should expect that in the first 2 packets of the handshake. Remember, the acknowledgement number is telling us the other side's next expected sequence number, what we expect to see from the other side. And as you work with TCP communications, don't forget that Wireshark also has this sequence and acknowledgement analysis section. Now I need a little more real estate on this screen, so I'm going to turn off my packet bytes view so that I can see everything in the TCP header. Remember that anytime you see it blue and underlined, it means that it's linked. So we can double click on something and go right to the next packet that's defined in here. So we have the handshake process that looks like it took place just perfectly. After the handshake process, we have the server sending back the FTP banner. Now the server is at sequence number 1. And although this isn't an actual field in the packet, Wireshark is telling us what the next sequence number should be the next time this server communicates. It should be at sequence number 69. That means that there must be 68 bytes of data in this packet. In addition, if we look at the flags information, we can see that the push flag has been set for this communication, meaning don't buffer this on the way out and don't buffer it on the way in. This is very important. And we can see the server saying that its window size is 8,760 bytes. That's the receive window size. That's what the server could accept if the client began to send data up to that server without causing a congestion problem. And we can see that we have some sequence and acknowledgement information in here as well. We can see the relationship that this is an ACK to the segment in frame 5. Not only do we have data in this packet, but we also are acknowledging receipt of information from the other side. And this is our FTP information. We can see it says Chad's FTP server, authorized access only, technical reviewer, carriage return line feed. Now let's go to the client side of the communication, the next packet. Here the client is sitting at sequence number 1 still. That's the same sequence number it finished up the handshake with. We can see that Wireshark is telling us that the client's next sequence number should be 12. That means there must be 11 bytes of data in this packet. Again, we have the sequence and acknowledgement information, and there's our line of information, the data that's being sent across the wire. Indeed, we can see that there are 11 bytes of data being sent across. USER space FRED, and then the /R is 1 byte and the /N is 1 byte, which counts up to 11 bytes of data. Now in this packet, we can see the acknowledgement number field value has been set to 69. I'm going to choose to view the packet bytes for a moment. As we highlight this field, we can see where it is in the packet. The acknowledgement number field sits right after the sequence number field. So the next packet in this sequence is from the server, giving us an FTP response saying that the username is okay, I need a password. The server is now at sequence number 69, which is what the client expected and what the client set in the last packet's acknowledgement number field. We can also see that the server believes that the client's next sequence number is going to be 12. Our client knows that, and Wireshark already calculated that for us. The next sequence number for the server should be 104. And again, those bits of information that are inside of the brackets, those aren't actual fields. That's Wireshark's analysis of what's going on. There's the data crossing the cabling system. And let's take a look at the next packet. Here we see the client is at sequence number 12, which is what we expected, and the client is saying that it believes the server will be at 104 next. These sequence number and acknowledgement number fields are so important in TCP communications. It's the way we check for packets that arrive out of order or missing segments. Later on in this section, we are going to focus on handshake problems that occur up in the first 3 packets of that handshake process. We're also going to look at the TCP recovery process. So let's say, for example, the client sent this packet across with the user command and the username, and this packet didn't arrive at the server because we have sudden packet loss on the cabling system. We have a sudden disconnect. How does TCP recover from that? We're also going to look at congestion throttling. It has to do with not only the window size field right here, but how we handle packet loss on the cabling system. Now let's look at how this connection runs for a little bit. We'll sort of scroll through and see what else happens in here. And I also want to show you how the connection finally terminates. So as we scroll through, we can see this is the command channel that someone is using to send FTP commands, and then they want to open up a secondary connection because they want to do a directory listing. And the data has to go on a second channel. It cannot go on the command channel, so we have to have a second connection. And here we see another connection being established in the middle of this trace file on packets 23, 24, and 25. The first packet of the handshake process shows us that we have dynamic port numbers being used for that second connection. In addition, we can see that the second connection is established by the server, and the server's starting sequence number for that second connection is sequence number 0. Now that doesn't matter if we're using sequence number 0 during this connection and we're using sequence number 0 starting on the other connection. They're totally separate because connection information is a combination of IP address, the TCP port numbers, and the sequence numbers. So it doesn't matter at all when we try to reassemble data. We're not going to get confused between the two streams. Now in the SYNAC packet, we can see that we've got starting sequence number 0 coming from the client. Now this is a normal three-way handshake. We've got the SYN and the SYNAC and the ACK. But we have something different in this first handshake packet. In this first handshake packet, coming from the server has included 8 bytes of options. We have our maximum segment size, and we have NOP, NOP. That stands for no operation, or no option, no option. And then we have something called SAC permitted, and that stands for selective acknowledgement. I'll talk about that in just a minute. First, I want to bring up our hex view so we can see where each of these bytes sits. I'll scroll this up just a little bit more there. Now the maximum segment size field value, this option value, takes up 4 bytes to place this information in the options area. Since TCP calculates the header length as a multiple of 4 bytes, everything's got to end on a 4-byte boundary. But the SAC permitted option only takes 2 bytes. That's why we have the no op and the no op leading it off, to round this out and make sure that it ends on a 4-byte boundary here. Now the selective acknowledgement process indicates that this server, if it's sending data to you, it's sending packet 1, packet 2, 3, 4, 5, 6, 7, 8, and for whatever reason packet number 4 gets lost in the transmission process. You can send it an acknowledgement saying, listen, I was missing packet number 4. I expect number 4 next. And it will send you just packet number 4. It won't send you 4, 5, 6, 7, 8, the rest of the stream. That's called selective acknowledgement. And we like to see that in data communications. We don't want to see anything retransmitted unless we absolutely have to have it retransmitted on the cabling system. Now let's scroll down towards the end of the trace where the connection is being terminated. I'll scroll down, and here we begin to see a termination process. And this trace is nice because it shows 2 different types of termination processes. This first one is initiated by 10.3.30.1. That's the server in this case. And the server has sent the packet out with the fin bit set on. That means I'm finished with what I was doing. I don't need to send any more data across. There's the fin bit set to 1. Now in this packet, the server is on sequence number 138. The client acknowledges receipt of that packet by sending the ACK bit set to on. Now notice that the client is sitting at sequence number 1 here. If you see a communications sequence where someone is sitting at sequence number 1 all the way through, then you know that this device did not send any data out. They're still stuck at sequence number 1 all the way through the communication because the sequence number will only count up when data is sent from that device. Now we see packet number 36. The client is sending out a fin ACK to the server. And then finally, this closing process is finished by the server, sending out the ACK. Now in this case, we see that the server has incremented its sequence number. It's now at sequence number 139, whereas in packet number 34, it was at sequence number 138. There is no data contained in this packet. This is one of the phantom packets that we see during the handshake process and we see during the termination process. So I'll calculate this and make sure that this packet does not have any data in it. I'll open the IP header to see what the total length value is. The total length value is 40. Now that includes the IP header and any valid data that follows it and does not include any padding. In the TCP header, the header length field is 20 bytes. So we have a 20-byte IP header and a 20-byte TCP header, and there's no room for data in here. So we know that there isn't a byte actually in this packet. That's just the phantom byte. Now there's another termination process, which is interesting because it's a little bit different. This is a termination process being sent from the client. Here the client sends out a FIN/ACK to the server. There we see the FIN bit set and the ACK bit set. And we can see that the client is at sequence number 75 in this packet. The server sends back a FIN/ACK packet, and then the client finishes up almost like a three-way handshake. This is like a three-way teardown. The client finishes it up in packet number 42, and it's incremented its sequence number by 1, just simply because we have this phantom byte again. Now on this communication, which is the command channel, we can see that the client has sent data to the server. And you typically will see that on an FTP client because they have to send their username and their password as well as the command saying that they want to retrieve files. So this is a normal TCP communication. In the next sections, we're going to focus on abnormal TCP communications, including looking at TCP scans and lost segments, how TCP recovers from lost segments, or when retransmissions occur, or we have a problem with the handshake, or maybe one of the systems is experiencing congestion. It doesn't have enough received buffer space available, and it begins to advertise a window of 0. How do we recover from that, and how does the TCP keep alive process work? In this section, we're going to focus on general, unusual TCP traffic, such as segmented traffic, segmented TCP packets, port scans, the TCP echo process, and some really strange scans on the cabling system. But the next 3 sections also deal with unusual traffic, such as handshake problems and how recovery has to take place because we have packet loss, and how we deal with congestion on the cabling system. The first trace I'm going to open up is called port scan. Now in this trace, we can see that we have a packet being sent from 10.1.0.2 going to 10.1.0.1, and the destination port number is 1. It's a SYN packet, it's a handshake packet. Now I'll turn on colorization so you can see how ugly this really looks. Here we can see the handshake packets, the SYN packets, are colorized with a gray, and the reset packets are colorized with this red background and yellow foreground. So it really stands out to look at this pattern. We can easily see when the pattern changes. So there we have a completed handshake. And down here we have a completed handshake. So the colorization can be really nice when you're looking at Wireshark sometimes. So here we have a SYN going out saying, I want to connect to port number 1. And the target system doesn't support anything on port number 1, so it sends back a reset ACK. Then the 10.1.0.2 sends out another SYN. And the other side says, no, I don't do that either. How about 3? No. How about port 4? No. How about 5? No. And it keeps going that way until we can see that port number 7, we have an opening on port number 7. And that's something we really don't want to see because that's the TCP echo port. And anything that's sent to that port will be echoed back. It's another way of doing a connectivity test, but also somebody can inject a packet into the network from one system that supports echo to another system that supports echo and spoof the source of that packet and get these 2 systems to go back and forth and just keep echoing each other, going to the echo port and from the echo port. So it's really ugly. It's one of those things that we typically just have turned off. Here we can see a connection attempt to port number 8 and a reset coming back. No, I don't support anything on port number 8. Let's see how many of these packets are reset packets compared to how many of the packets are SYN packets. Now I'm going to create a filter based on all reset traffic. So I'll go down into one of the packets that has the reset bit set to on. I'll right mouse click and I'll prepare a filter based on the selected value. Again, I could have just applied a filter, but I want you to see the syntax. tcp.flags.reset == 1. And I'll apply that. And there we can see, if we look down in the status window, the total number of packets in this trace that have resets are 10. There are 10 reset packets. Let's see how many packets are SYN packets. Now I'm just going to use this same packet right here. I'll right mouse click, prepare this as a filter, but I'm going to set the SYN bit to 1. Apply it. And now down below we can see that 26 packets in this trace are SYN packets. Now let's open up another trace, and this one is called Strange Scan. Now I still have my filter in the background, and I want to get rid of that filter so I can see everything that's going on. So I'll clear the filter. And here we can see right away we've got some of these packets colored in black. If you ever want to know why something is colored a certain way, you can look in the frame information and look at the coloring rule. The coloring rule, bad TCP. The coloring rule string is tcp.analysis.flags. So it's specifically because of the flag settings that it's being colored with a black background and a red foreground. Now the first packet that we see being sent out is a telnet. Looks like it's an attempt to talk to a telnet port, port 23. But look at the flag settings in there. Thin, SYN, push, and urgent, and that makes no sense at all. Thin means I'm finished. SYN means I'm refusing the connection or completely disconnecting. Push means this is really important information, don't buffer it. And urgent means look at the urgent pointer field for more information on how to read this data. That's completely nonsensical. But we do see that our target system did respond to that. We see that it sent back a packet saying reset ACK. So this would have worked for a connectivity test because the target would have talked back. So if somebody was limiting the ICMP echo communications, somebody could have used this type of a scan, a TCP scan, with these strange bit settings in order to see that the target was up. Here we see another packet with strange settings in the flags area. Again, this is something you shouldn't see on your network. And then we see the attempt again and a reset. So it looks like it's sending out the scan about every 5 seconds. That's something I hope you'll never see on your cabling system. The next thing we will look at is segmented TCP traffic. I'm going to open up a trace file called ftp-tcp segment. Now in this communication, it's an FTP communication, but we're not sending out the whole entire user command in a single packet as we saw in the last module. Here we see someone sending out an FTP request, and all they're sending out is one character, the letter U. If we go to the IP header, we can see that there are 41 bytes in this packet. 20 bytes will be the IP header, 20 bytes will be the TCP header, and there's only 1 byte of data actually being sent out. There's my TCP header. It says that the header is 20 bytes long, and as we scroll down, we can see there's the data. That seems very strange. If we look a little further, we can see there's the letter S being sent out, there's the letter E being sent out, user space F R E D. So it looks like someone is trying to send this TCP communications across the wire, and they're segmenting it. They're not IP fragmenting it. They're actually segmenting the TCP communications. One nice thing about Wireshark is that we can quickly reassemble that data. I'll right mouse click and say that I want to follow the TCP stream. And that's what's actually going across the cabling system. We can see that FTP service, there's the banner, and then the client is sending user Fred. Now that took a lot of packets to send user Fred, and it took a lot of packets to put in a password of Kruger, and it took a lot of packets to do quit. That is abnormal communications. We don't like to see TCP segmented traffic across the cabling system. Are they trying to get through a firewall or something? Wondering if that firewall will do TCP segment reassembly to figure out what's really going on? So that's another data pattern that we don't want to see on the cabling system. In the next section, we're going to look at handshake problems. Now the trace file we're going to open up is called TCP-handshake-problem. Most of the time when you're troubleshooting TCP handshake problems, it's going to be because someone is making a handshake to a target system, and the target system turns around and sends a reset back because it's not offering those services. That's not the case in here. I'm going to get rid of the hex portion down below because we don't need to see this. So I'll go to View and Packet Bytes and get rid of that. So here we see a handshake beginning. We could see a SYN, and the handshake is coming from this 67.161.32.69, and I'll refer to it by just the last byte value, going to this target system that has the last byte value of 19. We see a SYN-ACK come back, and then the ACK. So everything seems to be fine with the handshake. Then we see the client system send a packet across the wire with the push flag set and the ACK flag set. So far everything seems to be fine. Now we see a retransmission though. All of a sudden the client is sending that push ACK across the wire again. And we can look down in this bottom window and see that this frame is a suspected retransmission. Yeah, I would say so because the sequence number is 1. Even though there was data in that frame, the sequence number is sitting at 1. So we know that this is a duplicate of packet number 6. Now I know there's data in this frame because when I scrolled down it said that there was 14 bytes of data, and looking at packet number 6, that had 14 bytes of data as well. So here we have sequence number 1 going out twice with 14 bytes of data in it. Yes, this is a retransmission. Now the next packet that we receive is kind of strange, and I'm going to get rid of the colorization because it becomes too confusing to look at the colorization on some of these. So packet number 8 is a SYN-ACK packet. In fact, this is another version of packet number 4. We have 2 SYN-ACK packets coming across the wire. We don't see any analysis information on this one because Wireshark isn't quite sure what's going on at this point. This is strange that after the handshake has been established, suddenly somebody is saying, well, wait a minute, I actually didn't finish it. So this system is sending a SYN-ACK. Now the client is sending a duplicate acknowledgement. This packet, this duplicate acknowledgement packet, is a duplicate acknowledgement to the ACK that's contained in frame 7. So this is the same thing as frame 7. We see a retransmission across the cabling system, the client retransmitting, but look what keeps coming from the server side. The server keeps sending a SYN-ACK. The server can't even deal with the data packets going across because this server does not believe that the three-way handshake was ever completed. What was missing? What did the server not see? The server never saw the client's ACK packet. It's packet number 5 that is missing. And the server keeps coming back saying, hey, SYN-ACK, I think you're going to be at sequence number 1 next. Well, guess what? As the client is sending out data, just this standard push packet right here, it's at sequence number 1. There was no increment of the sequence number between packet 5 and packet 6, so the client can't even tell that it was packet number 5 that was missing and not packet number 6. And the client keeps trying to send packet number 6 across the wire, thinking that that was the one that was missing, and it wasn't. It was that third packet of the handshake that was missing. And all the way through this trace, you will see the client continues to retransmit sequence number 1 with its 14 bytes of data. The same thing that the client sent in packet number 5. Packet number 6. It keeps sending it because it's interpreting the server's SYN-ACK packet saying, look, I think you're going to be at sequence number 1 next. I'm waiting for that. And the client says, okay, I'll send you sequence number 1, but it's not the final packet of the handshake process. What a great trace to show how crazy things can get if you lose the last packet in the three-way handshake process. If we lost the second packet in the process, the client sends out, or the server sends out the SYN-ACK. If that was missing, our client wouldn't send that ACK packet out. So this has got to all appear to be correct from where you are sitting, but in this case, we can tell that the ACK packet was the one that was missing in this section. And even though we were taking the trace at the client, it looked to us like the ACK packet went, and then the client moved on to starting to send data up. What a great trace that is. Now we're going to focus on how the TCP recovery process takes place. So for example, in the case of packet loss, how does TCP recover from that? And we know that TCP is tracking sequence numbers and acknowledgement numbers all the time. So we're going to open up a trace called download-bad. When you look at that trace, you'll see, if you scroll through it, some window update packets. But we're going to deal with that in the next section. Scroll down until you see packet number 130. Now, in packet number 133, we see a notation from Wireshark saying that the TCP previous segment was lost. In this packet, we can look at the sequence number. Now, this is how Wireshark tells that a segment was lost. It looks at these sequence numbers, and it keeps track of what the next sequence number should be. And when it sees that we skip one of those sequence numbers, then it says, we've lost a packet. So let's go to the previous packet and see what the sequence number is. In packet number 132 from our server at 61.8.0.17, we can see the server is at sequence number 111290, and Wireshark says the next sequence number should be 112750. When we go to the next packet, the server is at 114210 though. We're missing a packet. We expected to see this 112750, but we jumped and we missed a packet. Here we could see the client sending an ACK packet, and the acknowledgement number field is what we expect to see next from the server. The client is sending the ACK value of 112750. Remember, that's what we expected to get next from the server. So the client is acknowledging receipt of the packet 132, saying, hey, I got this one, and I think 112750 should be next. That's not what happened, though. So the client sends an ACK for the packet that was in order. The server is sending out additional data. Now the server is sending out sequence number 115670. The server is moving on. The last packet the server sent out was 114210, and now the server is just sending out the next one. The server doesn't know that the client hasn't received a packet yet, but the client continues to send the same ACK for the last packet before the lost one. Here's a duplicate acknowledgement. This ACK packet is the same as the ACK packet in packet number 134. We can see that it says TCP dup ACK 134. The 134 indicates what packet this is a duplicate of. So here the client says, hey, look, I got your last packet, but where is 112750? We could see another duplicate ACK packet. I got your last packet, but where is 112750? And we can see the client continues to send these duplicate ACKs on the cabling system. As we look at the server side, we can see that the server just keeps sending data, possibly because if we have high latency, the server hasn't even received these duplicate ACKs yet. The server's just streaming out the data just like normal, has no idea there's a problem yet. When the server receives the original ACK and two duplicates, at that point the server will retransmit the lost packet. So here In the middle of all of this problem, we have another notation saying the previous segment was lost. So here we've got the server in packet 161 sending out sequence number 134,650. We expect 136,110. But it goes to 137,570. So we've got another packet lost. We still haven't even recovered from the first one. The client has already sent 16 duplicate acknowledgments. Somewhere along here, the server's got to retransmit that lost packet. And unfortunately, look, we have another packet lost in this whole sequence of events, and another packet lost. This is a terrible, terrible problem on this cabling system. Look how many duplicate acknowledgments the clients get across the wire to the server, till finally we get this thing called a fast retransmission, which is not so fast. But there is our sequence number 112750 that was missing from before. So in this case, the client said that was the one piece I was missing, and the server eventually sent that one piece. It didn't stop the data streaming from coming down to the client. The client could still accept the data, but the client kept saying, I'm missing this one piece. Unfortunately, in this connection, we have a lot of data loss, and it makes for a really ugly communication. Look at all of these duplicate acts going on. Let's see exactly how many duplicate acknowledgments occurred and how many retransmissions and how many lost segments. I'll select Analyze, and I'm going to go to the Expert Info Composite window. Now, according to the Expert Info Composite window, we have 0 errors. That would be things like malformed packets. We have 2 warnings. There we go. Previous segment lost. It says it's common at the capture start, but guess what? We cut everything from the handshake on, so it's not common. And the count, we had 100 packets that were lost. 40 fast retransmissions. We'll go to the notes section, and there we can see the duplicate acts. Now they're grouped together. Every time a packet is lost, we go through the process of sending a duplicate act. So we can assume that the duplicate act process started at least 78 times there. 68 times we had to go to a duplicate act 2 before we got the packet. 61 times we had to go to a duplicate act 3 before we got the packet. This should count down in numbers. It shouldn't ever count up, because at some point maybe we only have to send out 5 duplicate acts to get the packet. Maybe you only have to send out 3. Let's see how high the top number is on duplicate acts. Oh, that is ugly. There was one time when the client had to send out 48 duplicate acknowledgments to get a missing packet, and that's terrible. But TCP can recover. It's built into it to recover by sending these duplicate acts saying, I was missing this one, I was missing this one, I was missing this one, and you just keep hounding the other side until you get the packet that you were missing. Now this is a download process where things didn't go well. I want to open up the trace of an upload process where data is flowing the other direction to show you what happens when we have packet loss. I'm now going to open up a trace called IO-FTP upload. And in this case, we have the data channel of an FTP communications. In other words, we're not looking at the command information hitting port 21. We're looking at the secondary connection that's been established to transfer data from an FTP client to an FTP server. And it starts out looking really good. We have a nice handshake process that occurs. Now the data is being sent from the client up to the server. So after the handshake process occurs, then we see the client sending out a packet. Now if you want to see the data in that packet, I'll bring up the bytes window. There we go. So there we can see data down there being transferred in that packet. So the client sends data up to the server, sends more data up to the server acknowledges it, great. Client sends more data up to the server. Then all of a sudden we get a duplicate acknowledgement. The server in here is saying, look, I'm missing a packet. I'm going to bring this window up a little bit more, scroll this up for us, and I'm going to get rid of the data bytes window, the packet bytes, because we don't need to see that. In here, the server is saying, hey, I'm still at sequence number 1 because I'm not sending any data, but I'm missing your sequence number 1461. I expected to see that one next, so where is it? Well, did our client even send that? Let's look back at some of our client's communications, see if it sent that packet. Going to the client in packet number 8, it's at 4381. Go back again, it's 2921. Go back again. Well, our client sent 1461 across the cable, but the server didn't seem to get that packet. So the server saying, look, this is a duplicate acknowledgement. Now this is saying that it's a duplicate acknowledgement. It's a copy of packet number 6. This is the first copy of packet number 6. So packet number 6 is the first time the server said, hey, I'm expecting 1461 next. Sure enough, that's correct. So there's the first duplicate acknowledgement. There's the second duplicate acknowledgement, and here's the server or the client responding to that by sending that packet up. He says, oh, I'm really sorry. I didn't know you were missing 1461. Here you go. Now, the next packet we see from the server is saying, listen, I'm at sequence number 1. I expect to see 2921 next. Well, the client says, I know I sent 2921, but we see a retransmission. The client says, well, I'll send it anyway. Now the server says, well, now I expect to see 2963 next. And even though the client has already sent that packet out earlier, it's going to retransmit that packet on the cabling system. It's not waiting for duplicate acts here. It just figures, you didn't get it. Something's wrong with this communication. So the client retransmits everything up until the point where we're back to where we were before all of this retransmission began to take place and we lost a packet. This is really ugly because in this case we aren't just getting a single packet, but we're getting multiple packets retransmitted. If we look earlier at the packet that the server sent, the server said, I got 1461, but the client was already moving on to other packets and sending additional packets on the wire. So the server's a bit slow in doing those acts, and the client just figures, you know what, you didn't get these other ones, I'm going to go ahead and send them. So the client is acting as if that server can't handle selective acknowledgments. In other words, it figures that the server is going to need everything that was out on the wire up until the point when it found out about a missing packet. So that client is sending every single packet again, even though it doesn't see the duplicate acknowledgments on the wire. Let's look at the handshake process and see whether or not that server supports selective acknowledgement. Now in the first packet we see the client talking to the server, and the server says, hey, selective acknowledgement is permitted. I understand that. I can work with that. The server in the second packet of the handshake does not say anything about selective acknowledgement. So unfortunately we go to the lowest common denominator between the two devices communicating. And because of this, this client is going to send out every one of those packets up to the point when the sequence and the acknowledgement information is in sync again. What a bummer. That's a lousy communication. Now I want to open up another trace file where we have out-of-order segments, and I'll show you how TCP deals with that. We're going to open up a trace called download good. I know that sounds strange to have a trace called download good that has out-of-order segments, but it's really not a big issue in TCP communications. Now, rather than scroll through this trace to try to find the out-of-order segments, I'll select Analyze, Expert Information, and I'll go to the Warning section. And here I see one notation that there's been one packet that's out of order. So I'll open this up, and it says that packet number 12 is the one that's out of order, and in the background it's highlighted packet number 12 for me. So I'll close down the Expert composite window. So here is packet number 12, and in this packet we have a communication where this system is saying, wait a minute, something here is out of order. So I'll scroll down. We can see this frame is a suspected out-of-order segment. Well, let's see what segment it is. This is sequence number 2921. Next expected sequence number is 4381. I'm only interested in packets coming from this device to see what the order was in sequence numbers, to see if we really did have one that came out of order. I'll go to the IP header and apply a filter just based on, let me bring this up a little bit. I'll apply a filter just based on the source IP address. This time I'm just going to do apply a filter and then selected. Now I can see all the traffic sent from this device. And you can see not only do we have an out-of-order segment, but there's a notation that the previous segment was lost, which makes me think that that out-of-order segment probably should have gone before packet number 9. So let's start at packet number 6 and look at our sequence number and acknowledgement number values. I'm going to collapse the IP header. Now, packet number 6, we are at sequence number 1, and our next expected sequence number is 1461. Packet number 8, we are at sequence number 1461. The next expected sequence number is 2921. Packet number 9, we are at sequence number, sure enough, 4381. Next sequence number expected is 4384. And then packet number 12 was the one that was out of order. But you know what? It doesn't matter. The client isn't going to freak out about this because this kind of thing happens every once in a while. It's not totally unusual. But if you have too many of those, you might want to watch out for this. Typically imagine that your system is sitting at your office and you're communicating through the internet to a web server and you're downloading pages. There are multiple paths that traffic can take on the internet. Some paths are faster than others. So you might find that every once in a while you have packets that arrive out of order. TCP moves right along with that. It's not a problem as long as the packet arrives within a decent amount of time. TCP just reassembles it and figures, oh, we just got out of order. It's not a big deal. But if you look through your traces and you're communicating with an internal server, let's say, and you get a lot of packets that are out of order, then you might want to look at what's happening there, because if we get a lot of these out of order packets, maybe somewhere along the network we've got some sort of an asymmetrical routing problem going on, where packets are going one direction, sometimes going another direction the other time, and it's causing things to arrive out of order. There may be some communications that don't handle it as well as TCP does. So in that case, you might want to fix the problem if you see that you have a lot of these out of order TCP segments. In the next section, we're going to focus on TCP congestion throttling. And we'll look at systems that have a 0 window available. So they're literally saying to the other side, I can't accept any more data, I'm full. And we'll see how it recovers from that. Now we're going to focus on TCP's congestion throttling. Now when packet loss occurs on the network, the actual window of data that's allowed outstanding on the cabling system is going to be divided in half. But the clients can also throttle back the window based on their received buffer size. The trace file that I've opened up is called download-bad.pcap. Now, I know that there's a lot of packet loss in here, but some of the problems might also be due to the fact that the client's window has gotten down to 0. So all of a sudden the client says, I can't handle any more traffic. I want to check this out. So I don't want to go scrolling through looking for any window problems in here. I'll select Analyze, Expert Info Composite. And this is in the Notes section. Now we can see duplicate X, so we know that there's packet loss going on. I'm going to sort the summary column. Click it twice. And now we have the 0 window information comes up on top, window update comes up on top, and window full comes up on top. Now window update will happen a lot of times in the trace. So when a client has a lot of data coming down to it and it's filling up the buffer space, and then all of a sudden the application takes the data out, there's a big chunk of free space available all of a sudden, and the client will suddenly send a message across to the server to say, hey, you know what, window update, I now have actually a lot more than I had just in the last act that I sent you. So we expect that to happen all through here in the communications. So there we've got a lot of those window updates. We're more concerned about this 0 window, and the window is full information, because we don't ever want to see that in a data transfer. First, I'm going to open up window is full and show you that that occurs on packet 363. In the 0 window, we open that up. 0 window occurs on packet 364. And 366, and 368, and 370, etc. Now, usually you will find that a window is full message will occur before the 0 window, because the window is full message is coming from the server saying, you know what, based on the window size you last gave me, when I send you this packet, your window is going to be full. So the server knows that. The window is 0 comes from the client saying, you know what, I have no buffer space available. So I'm going to click on packet 363 listed in the composite area, and Wireshark has highlighted that packet in the background. Now look at all this black background communication. That's of concern, certainly. So we have this section in the trace where it doesn't look very nice at all. So let's look at what happened just leading into this. Now, our server is 61.8.0.17, and our client is this 10.0.52.164. So as I mentioned before, the server knows that sending this packet down to the client is going to take up all the available window space, the buffer space. It's going to completely fill it up based on the last thing that it heard from the client. So let's go up to the client, to the last thing that client said. Now bring up this window so we can look inside the TCP header. Here the client is saying that I have a window size of 2920 bytes, and it says it's scaled. Now, after we go through this, I'm going to go through the handshake process with you and show where the client has window scaling enabled. But basically this says from the client side that the client has 2,920 bytes available in the received buffer. The server sends a packet down. Now, this packet, it's at sequence number 295250. It's going to sequence number 296710, so we know that there are data bytes in there. And if we want to see how many data bytes, we can go to the IP header, get that total length field. So we know it's 1,500 bytes here, and we've got to subtract the TCP header and the IP header. So 1,460 bytes of data are contained in this packet right here, packet number 362. So we know the client's only got, what did we say? The client said it had 2,920 bytes. Packet number 362 from the server took up 1,460 bytes of that, and packet number 363 took up the remaining bytes. So at this point, the server says, you know what? I know that this is going to fill up the rest of your window. And sure enough, the client turns around and sends back a 0 window size packet. Now, that typically means that that client has an application that's really slow in picking up that data. So unfortunately, we've got to wait for this client to free up some buffer space before the server can send down any more packets. Now, the time value that I have set there is not correct. You can see you're not ever allowed to send packets back to back. But what I've done is I've changed the granularity of time. I'm going to go up to View, Time Display Format, and set it to Automatic. Now it breaks this all the way down to the microseconds, and we can see how much time occurs between those packets now. We can see the window full packet, and then we see 41 millionths of a second later the client says, yep, you're right, I have no window available. Now at this point, the client doesn't want to disconnect from the server, and the server doesn't want to disconnect from the client. So we go into a process called TCP Keep Alive. Here we see a packet coming from the server saying that this is a TCP Keep Alive packet. So the server is on sequence number 298169. And it says to the client, you're going to be at sequence number 446 next, because remember, data isn't flowing from the client. Now this packet has no data in it, and we can confirm that by going to the IP header and seeing that the total length is 40. 20 bytes for the IP header, 20 bytes for the TCP header. The client responds to that by sending back a TCP 0 window packet again, saying, listen, I still have a 0 window size. If we look in the IP header, we can see there's no data contained in this packet at all. Close this up. And the server sends another packet across. Basically, they're just sort of sending those back and forth to keep the connection alive. I'll scroll down, and look how much time was wasted by the client system being so slow that it can't get the data out of that TCP receive buffer. Let's measure how long that took from the moment that the client first said, I have no window available, until the point when it recovered from that and the client did have a window available. I'm going to go up to View, change the time display format. Now the first packet that I have in here, packet 364, I'll right mouse click and I'm going to set the time reference on that packet so that time starts with that packet. Now I can scroll down through this whole entire process until I hit the point at which we have recovery. Now we aren't going to have recovery until that client suddenly starts sending this window update packet across the wire. See this window update packet in packet number 367. Window update in this case is our client suddenly saying, hey, I've got a little bit of space there. I've got 3,760 bytes available. And it immediately sends another one saying, you know what, actually look at this. This application just took everything out in a chunk, and now look how much space I've got. 256,960 bytes available. But look how long that whole process took. Over 32 seconds. That's terrible. And most likely that's caused by an application at the client side that is so slow picking that data up that it's causing problems in the whole entire data transfer. So watch out for these windows and the zero window and the window update process. You should hopefully never see a zero window advertised across the network, because if you are seeing that, someone's completely refusing to receive data across the wire, and it's going to slow everything down. Now I want to go to the beginning of this trace to show you the setup of the window between the client and the server. This is the client's SYN packet, the handshake packet to the server. The client makes a handshake to that server, and during the handshake process, we can see that the client says the maximum segment size is 1,460 bytes, and there's no operation, and then we see a window scale of 2. A window scale of 2 means multiply by 4. A window scale of 0 means multiply by 1. So here, basically it's saying multiply my window value by 4, and that's how much received buffer space I have available, which is an awful lot. That application must be incredibly pathetic to not be able to pick stuff up when you've got a client that has such a big window size. Now at this point, I've got window scaling turned on, which it's turned on by default with Wireshark. So the next time this client communicates, we'll see what the actual window is, because Wireshark will do the multiplication for us. So in packet number 3, there we see the maximum window size, 256,960. That's the full window from the client, and that's how we can see in that communication that the application took everything out of the TCP buffer space and said, oh, the whole window's now available, everything's fine now. Still, that's awful. Let's look at the server. If the client had decided to send a bunch of data up to the server, what's the window size available at the server? Well, the server says, I have a window size of 5,840 bytes. And look at that window size. Wow, a window scale of 7. That means that we multiply the window size value times 128. So that server is available to receive a lot of data because it has this huge receive buffer set up on it. So the things we want to watch out for in this area would be lost packets, because that immediately reduces the actual window size on the cabling system, how much data we throw out on the cabling system, because we know that we're getting packet loss. And also we want to watch out for things such as the window being full. We really never want to see a window full condition. That always is a sign that things are going to slow down. So when we see a window full condition, then we see the client go out with a window 0, and then we see these keep alives take place. And all of that is going to slow down the data transfer tremendously.